Up till now, when we spoke of data and measurements, we thought of things like 9.1, 9.2, or if we got a more precise ruler, 9.15, or maybe even 9.153. This is continuous type data. However, we often have data that's discrete, that is, whole numbers. How many people came to our meeting? 15. Never 13 and a half or 12.97. It's always a whole number. This is count data. The distribution, the normal distribution that we've been working with, sometimes doesn't work very well with that kind of data. There are other distributions that do work well, and one of the most interesting ones is the binomial distribution. And that's the one we're going to be working on today, the binomial distribution. First, let me say, when should we use the binomial distribution? The binomial distribution comes into play when we have a dichotomous situation. A dichotomous situation means there are two possibilities. I like to call it success or failure. Nothing really about success. It's just a way of showing that there's two possibilities. You might use true or false. You might say heads or tails. That's a dichotomous situation. Boy or girl, children being born, they're either a boy or a girl. Dichotomous situation. Switches are on or off, a dichotomous situation. You pass or you fail, dichotomous. Plus or minus, the signs, plus or minus, dichotomous situations. There are many, many dichotomous situations occurring in nature, and binomial is the most important way to work with them. So let's learn a little bit about this binomial distribution. There are a couple of parameters to talk about. One of them is called the number of independent trials. Now that word trials really is left over from when this thing was first invented, and you can think of it as a trying to do something, in the sense of I'm trying to flip for heads. I'm flipping a coin, and I win if I get heads, so I'm flipping 10 times. I'm 10 tries to get me heads. So I'm trying to get heads. And N is the number of independent tries at doing something. P is the probability of a success. Whatever you want to call a success, it really doesn't matter whether it's success or it's true or it's false or it's boy or it's girl or it's plus or it's minus. It's one of the two possible things you're working with. The probability of one of these things is P on each trial. That is, if I flip a coin, here I have a coin, flip a coin. Half the time I'll get heads, half the time I'll get tail. The probability at each toss of the coin, at each trial, is 1/2. 1/2 for heads, 1/2 for tails. Let's say heads is success, okay? The probability of flipping a head, a success, on each and every flip of the coin is 1/2. So we got a 0.5 for this P here. And how many flips do I take? Well, let's say I flip the thing 10 times. Then I make 10 trials. They're independent because the flips don't depend on one another. I'm making 10 separate flips. So I have 10 independent flips of the coin. On each of these coins, the probability of a success is 1/2. So we have N independent trials, P, the probability of success on each trial. And what we're interested in finding is X, the number of successes in the N trials. How many heads did I flip in the 10 flips of the coin? How many of them were heads? I flipped the coin 10 times. Each head had a 1/2 chance of being heads. Each flip had 1/2 chance of being heads. How many heads did I get? X is the number of heads I got, or how many successes that I got in the N trials. Now we usually call that's the probability of X, X being how many, and with the parameters N and P. We know what N and P are. Sometimes it's written BX of N and P. That is, we know this is a binomial distribution, so for probability they often write B instead of P. What we do to get this is we specify X, how many heads I'm interested in, how many trials there were, and the probability of success on each trial. In our example, this would be a half, this would be 10, this would be a half, this would be, well, how many heads do you want to get in a 10? 8, okay, what's the probability of 8 heads if I flip a coin 10 times, and the probability of heads on each is 1/2? I then work it out, and I come up with a number here. That would be a binomial probability. And let's get right to it. let's just do it. Let's not wait around. Let's do the thing. Let's take 2 coins, or if you prefer, 1 coin, and flip it twice. You can either flip 2 coins or 1 coin. I like to think of 1 coin, flip it twice. Flip, not like that. You really have to flip it so you can't tell what it's going to be. And you flip it once, and you flip it twice, and what is it? Well, n is 2 in this situation, and the probability of success on each toss of the coin is a half. So we have a binomial situation. Dichotomous situation means it's going to be binomial. And n is 2, p is a half, and what we want to find is those probabilities. The probability of the only things we can think of is 2 heads, 1 head, or no heads. Those are the possible values for x. So x can be 2 heads, x can be 1 head, x can be no heads. What is the probability that x is 2, x is 1, x is 1? What is the probability, x is 0? What is the probability of flipping 2 heads in 2 courses? What's the probability of flipping 1 head in 2 courses? What's the probability of flipping no heads in 2 courses? Let's work it out. I'm going to uncover the page, and we'll see what we have here. If I have 2 coins, or I flip a coin twice, once and then again, there are only 4 possibilities. Either I flip a head the first time and a head the second time, or I flip a head the first time and a tail the second time, or I flip a tail the first time and a head the second time, or I flip a tail the first time and a tail the second time. Those are the only 4 possibilities. We already know that they're equally likely, but let's forget that for a moment. We'll prove that they're equally likely. The first coin has a 1/2 chance of being heads. So 1/2 the time, that coin will be heads. Now, for that first coin, half the time it's heads. How often will the second one be a head? Well, half the time the second one will be a head, and half the time it'll be a tail. So the probability of getting heads and a heads is a half and a half. For this half the time will be heads again, and that will be 1/4 of the time. So 1/4 of the time I'll get a head and then a head. That is a half for this head and a half for that head, and 1/4 of the time, then there'll be 2 heads in a row. How about a head and then a tail? 1/2 the time I'll get a head. And after I get that head, 1/2 the time I'll get a tail, the other half from here. So 1/2 times 1/2 is 1/4. 1/4 of the time I'll have a heads and then a tails. What if I get a tail first? Well, that half the time I'll get a tail first. And after I get that tail, half the time I'll get a head second. So half the time I get a tail, half the time I get a head after it, 1/4 of the time I'll get a tail and then a head. I can also get a tail and then a tail. 1/2 the time I'll get a tail. And after I get that tail, 1/2 the time I'll get another tail. Or 1/4 of the time I'll get a tail. Now, let's answer the question, what is the probability, what proportion of the time will I get 2 heads? Well, I can only get 2 heads if I get a head and a head, and that will occur 1/4 of the time. So that is the probability of 2 given 2 and 1/2. Okay? Now, let's go down here. This is 1. Why is that 1? Well, I get 1 head if I flip a head and a tail. I'll have 1 head if I flip a tail and a head, and then a head. So I can get a head. I can win if I win when I get only one tail, 1 head and 1 tail. I will win either case. 1/4 of the time I'll get the head first. 1/4 of the time I'll get the head second. 1/2 the time, 1/4 plus 1/4, 1/2 the time I'll get a head and a tail. Not worrying about when I got which, but half the time it will be a head, 1 head out of 2 flips. No heads out of 2 flips. Well, that's a tail, and that'll occur 1/4 of the time. And so we've worked out the probabilities that we're talking about for this situation. For this situation, n equal 2 and p equal a half. No matter what the situation is, it doesn't have to be coin flipping. It could be any boy. All right, let a success be a girl child. What is the probability of getting 2 girl children with? You have 2 children in the family. What's the probability that both are girls? The answer is 1/4. I have 2 children in the family, each 1/2 chance of being a girl. What's the chance I'll have exactly 1 girl? 1/2. Half the time I'll have exactly 1 girl. 1/4 of the time I'll have 2 girls. And what are the chances of having no girls? Well, 1/4 of the time I'll have no girls, no successes in 2 tries, when each success has probability 1/2. So it doesn't have to have anything to do with coins. Anytime we have a dichotomous situation where n is 2, and p is a half. There are only 3 possible x values, and here are the probabilities. Well, that's easy enough. Let's be harder about it. Let's take n of 2 and p of 3/4. Now, we no longer have a coin. We're flipping something. We're playing a game with, let's say that we invited 2 people to a meeting, and we figure that chances that they'll show is 3/4. Each one has a 3/4 chance of showing. John and Jane are invited, and there's a 75% chance that John will show up. There's a 75% chance that Jane will show up. Okay? Only thing that could happen is they both show up, one shows up, or neither shows up. Okay? Let's find the probabilities. And it doesn't matter whether we're talking about people showing up or flipping a coin that's unbalanced or anything else, as long as n is 2 and p is 3/4. Okay? So for n of 2 and p of 3/4, there are 4 possibilities. We can have 2 successes, a success and then a failure. That is, they both show up. Jane shows up, but John doesn't. Jane fails to show up, but John shows up. Neither show up. Okay? Now, what's the probability that Jane shows up? 3/4. There's a 3/4 chance that Jane shows up. Now, given that she showed up, what is the chance that John will show up? There's a 3/4 chance that John will show up. Well, 3/4 of the time of 3/4 of the time is 9/16 of the time. So 9/16 of the time they'll both show up. How about Jane showing up? That's 3/4 chance. But given that Jane showed up, there's a 1/4 chance that John won't show up. So then 3/4 times 1/4 is 3/16 of the time. Jane will show up, but John won't. There's a 3/16 chance that Jane will show up, John won't. Jane doesn't show up. Well, there's a 1/4 chance of that happening. But John does show up. There's a 3/4 chance of that happening, given that this one's happened or hasn't happened. So there's a 3/16 chance that Jane won't come, but John will. And there's a 1/4 chance that Jane won't show up, and there's a 1/4 chance that John won't show up, and together there's a 1/16 chance that neither will show up. Well, again, this is 2 people showing up, 9/16. This is nobody showing up, 1/16. This is 1 person showing up. 1 person shows up at my meeting. Either it's Jane and not John, or John and not Jane, and Jane shows up 3/16 of the time without John, and John shows up 3/16 of the time without Jane, and so the total is 6/16 of the time I will have 1 person at my meeting. And so the probabilities involved in this, that is, n of 2, p of 3/4, having nothing to do with people showing up or coins or anything in particular, just any time we have an n of 2 and a p of 3/4 in a dichotomous situation, the probability that there'll be 2 successes. Remember, the probability of each success is 3/4. The probability that there are 2 is 9/16. The probability that there are exactly 1 is 6/16. And the probability that there won't be any successes is 1/16. Okay, we're running right along, doing great. If you've swallowed it now, in fact, let me say this. I know some people are fretting about all the arithmetic involved here. It's not important that you memorize any of this. The important thing is that you understand what the ingredients are, where it's coming from. That you can sit down and redo it if you had to. You never will have to. The questions that I'm going to ask about this are all going to be quite simple. They're not going to be as involved as doing all this. What I'm going through these gyrations for is so that you can see what's done, the background, where these things come from, and therefore have a feeling for them. But I don't want you to memorize them. The answers that we get, 3/16, 1/16, totally useless, totally meaningless. There are so many different possible n's and so many different possible p's that you couldn't possibly remember all the distributions. So don't try and remember them. Just think about how they're coming about. And you see that they really don't depend on whether things are coins or children or people showing up. They're just probabilities having to do with a dichotomous situation. So let's look at one more situation. let's try n of 3 and p of 3/4. Now, that's a little rough, n of 3 and p of 3/4. Now, this will occur when there's 3 people showing up at our meeting, or anything which has a probability of 3/4 for each occurrence. And there are 3 occurrences. So there are 3 trials. The probability of each trial being a success is 3/4. There are 8 possibilities. There are 4 on this page. Let's look at the 4 on this page. You can have a success, and a success. But each success occurs 3/4 of the time. 3/4 of the time, this success occurs. Of that 3/4 of the time, you have 2 in a row. Of that 3/4 of the time, you'll get the third one. So that 27/64 of the time, you get 3 successes in a row. Here's a bunch of ways to get 2 successes. 2 successes and then a failure, success, failure, success, failure, success, success. Those are the only ways you can get 2 successes out of the 3 trials. And you can get them 3/4 for this success, 3/4 for this success, 1/4 for this failure. So that's 9/64. This success, failure will occur 9/64 of the time, or the chances of it occurring is 9/64. Success, failure, success, 3/4, 1/4, 3/4. 3/4, 1/4, 3/4. 9/64 again. Failure, success, success. 1/4, 3/4, 3/4. 9/64 again. So the probability of having 2 successes is, this is 3 successes. This is 2 successes, 9/64, 9/64, 27/64. It happens just by accident to be the same just for this example, but it's not usually the case. So we have 3 and 2 so far. Now we need 1 and 0. But there are other possible combinations. These are only 4 out of 8. The other 4 look like that. You can get a success and then a failure and then another failure. You get a failure, success, failure, 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 success. Each of these 3 are the same as saying 1 success. I got only exactly 1 success out of 3 tries. Well, this one occurred 3/4, 1/4, 1/4, or 3/64 of the time, or a 3/64 chance that I will have a success and then 2 failures in a row. I'll have a failure, success, failure, 1/4, 3/4, 1/4. So 3/64 of the time, I'll have failure, success, failure. Or the chances of having failure, success, failure is 3/64. Failure, failure, success, 1/4, 1/4, 3/4. There's a 3/64 chance that I'll have 2 failures and then a success. And all of these together mean I got 1 success. So what are the chances of getting 1 success out of 3 tries? Well, I can get it this way, or this way, or this way. 3/64 of the time I get it this way. 3/64 of the time I get it this way. 3/64 of the time I get it this way. Therefore, 9/64 of the time I have 1 success, exactly 1 success. The only thing left is having 3 failures in a row, and they occur 1/4 of the time, 1/4 of the time, 1/4 of the time. Put them together, 1/64 of the time, so I get no successes 1/64 of the time. And writing it out, if someone said, give me the binomial distribution for n of 3, p of 3/4, you could do it. We just worked it out. Having nothing to do with coins or anything else, just give me the probability distribution for n of 3, p of 3/4. This is the whole distribution. There are only 4 possible values for x. X can be 3, and the chances of that happening are 27/64. X can be 2. The chances of that happening are 27/64. X can be 1. The chances of that happening are 9/64. X can be 0. The chances of that happening are 1/64. They, of course, add up to 64/64. They add up to 1. All right, remember this for a moment. We're going to use these numbers in what we do in a moment or two. Here's how a statistician does it. We don't really go counting all those things, multiplying all those numbers. I'm using Minitab again. We say set C1, I put the number 0 to 20. Actually, I'm looking for the binomial for n of 20 and p of 0.35. That's what I want. I want all the possible x's, which is 0 through 20. So I put 0 through 20 in column 1. And my data, say, give me the probability density function of the data in C1, put it in C2, for the binomial distribution with n of 20 and p of 3.35. And here it is, spits it out. You see some of them on the screen. If I lift it up, you'll see the rest. Okay? So you've got all these probabilities. There's no chance of having 20 or 19 or 18, but you begin to get some probability, these numbers, and then the highest ones somewhere around here. Right? That's the whole distribution. Now, I'd hate to have to do this by hand. It would take you forever to do it by hand, but the computer does it in no time, flat. Now let's look at that distribution. Let's look at the distribution we had here. Remember, for this distribution, n was 20 and p was 0.35. And I plot. These are the heights. There's nothing in between. It's not a smooth curve like with the normal distribution. These are zeros, or very tiny numbers here. The middle is here at 7. 7's the middle. Well, notice the mean for the binomial is always equal to n times p. 20 times 0.35 equals 7. So it's not surprising that the center of this distribution is around 7, because the mean of the distribution, the center of this distribution, is n times p. So for the binomial distribution, remember that the mean is always n times p. All right? Okay, so now we've learned about the binomial distribution, and now we can use it when we need it. It's a very general distribution. It does not have anything to do with coins or children being born, and yet it has everything to do with them, because anytime you're in a situation where there's two possible outcomes, the binomial distribution is a very useful distribution. And next time we're going to use it. Have a happy.